Right. Now let us talk about Kirchhoff rules. What is Kirchhoff rules? When do we use Kirchhoff rules? First of all, we use Kirchhoff rules during the complex circuits. Yeah. For example, like we use these rules for complex circuits. Why do we say why do we have complex circuits? For example, like this one, if you look at here, in this circuit, we have not just one battery, we have multiple battery. We have 3 batteries here, and then we have this resistor also. I'm not sure this resistor 1 and resistor 2, are they in series or in parallel? Okay, I'm not sure what combination is this. Yeah, is it series or parallel? Yeah, and we have multiple battery at different loop. So this one definitely we cannot use the traditional method about the series and parallel combination. This one we have to use Kirchhoff rules. We regard this one as the complex circuits. Yeah. If you have multiple batteries, more than one battery, normally we use Kirchhoff rule to solve the questions. Right? Cannot use the traditional method. So anyway, this is very simple. Under Kirchhoff rules, it has 2 laws. Okay, the first law and the second law. Yeah, first law and second law. First law is called the junction law because it happened at a junction. The first law is about current. Yeah, it's about current. Current entering a junction and current going out from a junction. Okay. Second law is also called loop law. Yeah, it's called loop law because it happens in a loop. Yeah, it happens in a loop. This is about voltage. Okay, voltage, which is total E equal to total IR. The voltage supply equal to voltage consumed or voltage used. Okay, we will talk in details for each of these law. Now, let us first look at the first law. Yeah, junction law, about the current, current going into the junction and current going out from the junction. This one, this law fulfill the conservation of charge because we know that current is the rate of flow of charge, isn't it? Current is actually dq over dt. So current is actually charge. So the current that going in must be equal to the current going out. The charge must always be conserved. Yeah, cannot just disappear into nowhere. Okay. Okay. Let us look at this circuit. Okay, this circuit has 2 junctions, A and B. We call it junction because it has like 3 paths. You see, 1, 2, 3 paths. For points like here, this is not a junction because it is actually like it's actually like one road. Sorry, it's here. This is not a junction because it's actually one wire also. Here also not a junction because it's still a one wire. See that? This one not a junction, is still one wire. Yeah, it's still only involve one current. Yeah, for example, this point is still only one current, which is I2. This point is only one current, which is I1. So these are not junction. Okay, junctions are point where you have 3 current. Junction is you have 3 current, at least 3 current, not 2 current, not 1 current, at least 3 current. Okay, like for example, this point, point A is a junction. Yeah, you have 3 current, and point B also you have 3 current. So these are called junctions. Okay, let us look at junction A. So first of all, what current entering junction A? What current entering? It is I1 and I2. Yeah, and current entering is I1, I2. So that's why total current in is I1 plus I2. I1 plus I2. And then what current go out? It is the I3. I3. So that's the total current going out is I3. So the total current going in must be equal to total current going out. That means I1 plus I2 must be equal to I3. Okay, you cannot have all current entering a junction and then none going out. You cannot say, oh, it's impossible that I3 also going in. Yeah, we cannot say I1, I2, I3, all current going in, and then all the current disappeared into the point A, and then it goes nowhere. This is not about conservation of charge. Okay, so when there is current going in, like I1 and I2, there must be current going out with equal amount, which is I3. So I1 plus I2 must equal to I3. That means if I have current 1 ampere and 2 ampere going in, the current going out must be 3 ampere, must be equal. You cannot say, 1 plus 2 ampere and then suddenly got 6 ampere going out. This is impossible. Not about conservation of charge. How can you the charge become double or triple suddenly? This is not possible. Okay, so the total current in must equal to total current going out. And then look at junction B. Junction B, so the current going in is I3, so that's why total current in is I3, and then current going out is I1 and I2 again. You see that? I1 and I2. So I1 plus I2. So I3 equal to I1 plus I2. Do you see that these two equations, you compare between these two equations, this equation and this equation, they are the same. It's just invert. You see, I1 plus I2 equal to I3 with I3 equal to I1 plus I2, they are the same. So for normally for the question, you just choose one junction enough. Yeah, because you will get the same answer. You'll get the same answer. You want to choose junction A also can. You want to choose junction B also can. So you still get the same equation. Yeah, it's just like invert only. Yeah, if you see, this is how the current goes. As we can see, current I3 is the biggest current. I3 is the biggest current because it is a combination between I1 and I2. Yeah, I1 and I2 combined together become I3. And then I3 going out, split out again, it become I1 and I2. So you see how the current goes? The current I1 travel from point B all along the way and then go to junction A. So you see the orange color one is I1. And then the green color is I2. I2 going out from here and then go to junction A. This road is all current I2. And then I3 is the blue one. Yeah, travel in the middle. Okay, so you can see I3 going to the right, split into two, I1 and I2, and then I1 and I2 just go their own ways, and then I1 and I2 combine again at junction A. Become I3 again. So the process continues. Why there is current in this circuit? Of course, this circuit is not complete. Actually, it has battery. The battery that driving this current, giving energy for the charge inside the wire, for giving energy for the free electron in the wire, for the electron to flow in the circuit. That's why, because of battery, who makes the current flows, that's why I've got all this current. Okay, we will study about this more later on. Okay, let us now look at the loop law. Second law is also called loop law. It's called loop law because it happens in a loop, in a closed loop, in fact. Yeah, it must happen in a closed loop. Must be a complete circuit. Closed loop, cannot open loop. Yeah, must be a closed loop. So total EMF must be equal to total IR, which means that this is actually battery. Both of these are voltage. You understand? EMF is a voltage, and then IR also voltage, because we know that V equal to IR, isn't it? V equal to IR. We have voltage across external resistor. We also have voltage across the internal resistor. Okay. We have voltage across external resistor and also voltage across internal resistor, IR and IR. Okay. So let us look. This one is actually voltage supplied. Voltage supplied. The total EMF is actually the total voltage supplied must be equal to the voltage used. Used by the resistor. The total supply must be equal to total use by the resistor. Or in fact, actually this formula comes from the original formula, which is the E equal to IR plus IR. Remember this? It's the same with this formula, Kirchhoff second law, total EMF. Total EMF equal to total IR. Okay? This one, yeah, let me write again here. This one, total IR, actually include both external resistor and also internal resistor. So in fact, I should write it down here. This is actually the voltage supplied must be equal to voltage used. Voltage used in a complete circuit. So let's say if I have a complete circuit like this one, a complete circuit, I have battery E1 and battery E2. Okay, and then I have resistor. I have R1, I have R2. Some more, this one have internal resistor. R1, this one is internal resistor. Internal resistor for battery 1, internal resistor for battery 2. Okay. So the total EMF supplied by the battery, the voltage supplied by the battery must be equal to the voltage consumed. Let me write it. Total must be equal to the voltage supplied by the battery must be equal to the voltage consumed by all the resistor, by all these resistor, the voltage used for a closed loop. I can say for a closed loop. This is called a loop. The voltage supplied by all the battery must be equal to the voltage used by all the resistor. And this resistor include both the external resistor and also the internal resistor. Or we can also, in the other way, we can say that this is like the potential rise must be equal to potential drop across a closed loop, in a closed loop. Okay, in a closed loop. So energy, actually this is all about conservation of energy. Conservation. Second law is about conservation of energy. First law is about conservation of charge. Second law is conservation of energy. So actually we know that voltage is about energy, isn't it? This voltage supply is like battery giving energy for each charge that flowing through in the circuit. Yeah, actually the battery is there to give energy to all the electron that flowing in the circuit. Yeah, battery is the one who give energy to the electron that flow in the circuit, but the resistor, external resistor and the internal resistor, both they are using up the energy of the electron flow in the circuit. Okay, battery give energy for the electron to flow in the circuit, but the resistor, the external resistor and the internal resistor use up the energy of the electron that flow in the circuit. So the total energy supplied by the battery, must be equal to the total energy used by all the resistor in a closed circuit, in a closed loop. Okay. So it's the same. This it's like this formula. So E equal to IR plus IR. It's just that we not just have only one resistor, but we have multiple resistor, we have multiple batteries, we have multiple internal resistance. So that's why we cannot use this formula anymore. We use the total E equal to total IR because we have multiple batteries, we have multiple internal resistor, we have multiple external resistor. Okay. So it's the same concept. Yeah. So let us look deeper on how to determine the positive and negative sign. This is very important in Kirchhoff's second rule, the positive and negative sign. Okay, look carefully. Very simple. Same direction positive, opposite direction negative. That's all. That's all. Same direction positive, opposite direction negative. So first of all, before you do this question, you need to label some direction. Label some direction. For the battery, you need to label the direction from negative terminal to positive terminal. The battery has direction. You know, the battery has direction always from negative to positive terminal. Like you see the first battery here, negative to positive, the direction of this battery is to the right, because from negative to positive. Whereas for the second battery, the direction of EMF is to the left because from negative to positive. Okay, so for battery, you need to label the direction first, always from negative terminal to positive terminal. Okay, battery depends on terminals. Resistor depends on current. Don't say that battery also depend on current. No, let's say there is a current flowing here in through the current flowing through the battery also. Don't say that the battery depend on direction of current. This is wrong. This is wrong. That battery does not depend on direction of current. It depends on direction of the terminals, from negative terminal to positive terminal. But for the resistor, it don't have terminals, isn't it? No terminals, no positive, negative terminal. For resistor, it depends on current, the direction of the current. Okay, so remember, for battery, look at the terminals. For resistor, look at the current. So now how to determine positive EMF or negative EMF? Because we know that although we say that the battery supply voltage, supply EMF, but actually some battery, they're connected in the opposite direction. They're connected in the opposite direction. So the EMF actually go against the voltage supply. That's why it end up to have a negative EMF, because it not actually supply voltage. But in the other way around, it cancel the voltage. Some battery cancel the voltage. Yeah, it's like for example, like this circuit. You see, this circuit, yeah, connected in such a way that this battery go against the loop. You see that? Go against the loop. It's like you connect a two water pump. Like for example, one circuit like this. A battery is like water pump, isn't it? A battery is like water pump. Battery is like water pump. So for example, I have let's say I have two water pump in the circuit. I have two water pump. This water pump and the second water pump. This is the second water pump. Okay. This water pump, the first water pump is like E1. The second water pump is like E2. But you see that the first water pump, it rotate clockwise. It rotate clockwise. So that's why the current being pushed to the right. But the second water pump, it rotate in the opposite direction. It rotate in the opposite direction. Yeah, it's supposed to rotate in the same direction. Then it is helpful, isn't it? Sorry. Again, it's supposed the pump 2 should rotate in the same direction. Then the current will become stronger, isn't it? The current will become stronger. But instead, this pump rotate in the opposite direction. It rotate in the opposite direction. The pump 1 rotate clockwise, but the pump 2 rotate anti-clockwise. So it slow down the current. It make the current smaller. Because this one pump in the opposite direction. That's why even for battery, there are positive EMF, there are negative EMF. Positive EMF is really the voltage supply, but negative EMF means it cancel the voltage. It's like the pump acting in the opposite direction. So actually, diminish the current that flow through. Maybe the current now become lesser already. The current become lesser already because of the battery rotate in the opposite direction, connected in the opposite direction. Understand? So how to really determine whether it is a positive EMF? Yeah, like this one, like this case, this is a positive EMF. This case it is a negative EMF. So how to determine whether it's positive EMF or negative EMF? There is one way. There's one way by drawing the loop. By first drawing the direction of the loop, and then we compare the direction of the loop with the EMF. Understand? Compare the direction of the loop with the EMF. So look at here. Remember, battery, look at terminals. The direction of battery is negative terminal to positive terminal. Now, as I said before, same direction positive, opposite direction negative. Okay, so how to know is positive EMF? It is when the direction of EMF from negative to positive, same direction with the loop. Same direction with the loop, then you get positive EMF. But if the EMF is opposite direction to the loop, like this one, the EMF to the left but loop to the right, opposite direction, then you get negative EMF. This is like the water pump that pump in the opposite direction, which makes the current smaller. Understand? So this is negative EMF. So EMF and loop same direction, positive. EMF and loop direction opposite, negative EMF. Okay? How to determine direction of the loop? Later I will explain over here how to determine direction of the loop. Don't worry, step by step we will know everything. Okay? So that's what. And then for the resistor, also have a positive and negative EMF, and also have positive and negative IR. So let's look. For resistor, because it don't have terminals, we look at current. Resistor must look at current, EMF must look at terminal. So for resistor, look at current. So for resistor, we look at current, we compare current with the loop. If the current and the loop same direction, positive IR. If the current and the loop opposite direction, you will have negative IR. Okay, this IR is also voltage. Yeah, it's also voltage. It's called voltage use. Yeah, because V equal to IR. And this resistor can be external resistor big R or internal resistor small r. Yeah, we have IR big R, we have IR small r. Understand? So IR also have a positive and negative. Yeah, by comparing direction of the current with the loop. Same direction positive, opposite direction negative. So same thing, EMF and IR both use the same concept, same direction positive, opposite direction negative. Yeah, all we compare with the loop direction. Okay, now good. Now what is the problem solving strategy for Kirchhoff rule? First of all, we must label. This is the first most important step. Draw the circuit. You must draw out the circuit. Yeah, the question will give you this circuit diagram. You must draw again in your answer sheet. Draw again, and then you need to label. What do you need to label? Because we want, like for junction rule, you need to label the current at the junction. Need to label the current at the junction because we need to apply this formula. We need to know which one is current in, which one is current going out. Like you see, I label like this circuit. I already label the current. You see, current I1 going in, I2 going out, I3 going out. I label the current at the junction. At each junction, I need to label the current. Next, what I need to label? I need to label the direction of the EMF. EMF. I need all the battery. I need to label from negative to positive. From negative to positive. Direction of EMF, you need to label. You see, I also labeled, like for this question, I labeled direction of EMF. You see this? Negative to positive, I need to label this direction EMF, and this E2 also from negative to positive, I label this blue color label. You see the direction of the EMF, And E3 also I label negative to positive, direction of the EMF. And then what you need to label? You need to label the current at each resistor. You need to label the current at each resistor. So you see, the current I1. Okay, I label the current I1 near the resistor. And then this internal resistor also I label the current I1 passing through. For R2, I label the current I2 passing through. I3 also I3 passing through. The internal resistor R3 also I label current I3. Internal resistor R2 I label current I2. So you see, I need to label all this direction of EMF, direction of the current near the resistor, direction of the current at the junction. Because why? Because I need to build equation. I need to build the first law equation, current in, current out. And also I need to, for the second rule, I label the EMF and EMF for battery. I label the current at each resistor and external resistor and internal resistor, because I want to determine positive EMF or negative EMF. Because I need the direction which I label. I need the direction which I label to compare with the loop direction. If same direction positive, if opposite direction negative, I also need to label the current at each resistor, the external resistor and internal resistor, so that later on I can compare the direction of current and the loop to determine whether it is positive IR or negative IR. So label is very, very important because you need to build later on you need to use the label, the direction of the label, to build the equation for first law and build equation for the second law. Okay? And then second step, of course, is the first law. First law, we build the junction law. And then the second step, the third step is the second law. Second law is this one lah. Total E equal to total IR. We can build equation for second law. And then after that, in the end, we solve using calculator. I will talk about this deeper later on. Yeah, basically the strategy is just this 4 steps. The most priority thing is you must label first. Draw the circuit first. This circuit you must redraw in your answer script. Then you need to label the direction. First you label, then the rest of the step very easy already, because you all have all the labels, so easy for you to build the equation already. Yeah, finally you solve the equation. Yeah, it's a normally solve simultaneous equation, right? Now you have in the question, sometimes it will give you one loop, sometimes it will give you 2 loops. Question like one loop. This one is the one loop. You see that? I redraw again. Maybe I redraw again. One loop means is like this circuit, like this circuit, I give just now. This is E1, this is E2. Okay. Now and then you have a resistor. You have resistor R1. This is R2. Okay. I want to ask you, how many current is this in this circuit? How many current? How many? A very simple question. How many current exists in this one loop? This is a one loop. This is actually a one loop. Yeah, this is actually one loop circuit. One loop. Yeah, this is a one loop. One loop. This is one loop. So how many current in this circuit? Is it 2 battery? Then you have 2 current. Oh, some people will say, battery 1 produce current I1, battery 2 produce current I2, and then these 2 current travel down and collide with each other. Then suddenly here we have explosion happen. Oh my God! Is this your concept? The battery 1 produce current I1 and battery 2 produce current I2, and then because they travel in the opposite direction and then they bang each other and then collision happens and then suddenly the circuit in the middle here burn off. Is that what you think? Is that what you think, that battery produce current? Is it battery produce current? Wrong concept. I already told you before. Battery is not current source. Battery is not. Where is it? Let me show. Where is the battery? Is not a current. Battery is a water pump. It's not a current source, it's energy source. The free electron already exists in the wire. Yeah, in the wire already exists a lot of free electrons. You understand? Already exists a lot of free electron. Battery is not there to give out the electron. Battery is just to drive the electron, to move the electron in the circuit. Electron already exists in the wire. Battery is just there to give energy. To give energy for each electron so that the electron can move in the circuit. So battery is the energy source. It provides energy for the electron in the wire, in order for the electron to move in the wire. So battery does not provide electron. Electron already exists in the wire, yeah, because the wire is a conductor. Yeah, it has many free electrons. Battery is just there to move the electron that already exists in the wire. Understand? It's just like a water pump. The water already exists in a pipe. Water pump is not to provide the water. Water pump is just to move the wire. No, water pump is just to move the water in the pump. Understand? Provide energy for the water to move in the pump. To move in the pipe. Okay? Now, go back to here. So, wrong concept, you say that battery 1 produce I1, battery 2 produce I2. Don't say that, oh, you have 2 battery, then you must, if you have 2 battery, then you must have 2 current. Wrong. 2 battery, then you have 2 current is wrong concept. Okay, which is wrong. So what actually happened is, these two, if you look at here, these two, you see, this is like 2 battery, they are in opposite direction. Because later you do the positive EMF and negative EMF, you compare with the loop direction, then you will find out this E1 and E2, they are acting in opposite direction. So, actually, this is only one circuit. One circuit only have one current. You understand? But the direction of the current depends on the battery EMF. Let's say, which battery is the dominant one. Let's say E1 is 15 volt, but E2 is only 10 volt. Do you think which battery the current will follow which battery? Which battery is the dominant one? Of course, this E1 is a bigger pump. E2 is a smaller pump, isn't it? It's a smaller pump. So in the end, the current will be forced in the direction of the bigger battery. The current will be forced the current will follow the direction of the bigger pump. You understand? So only have one current. One circuit only have one loop, only have one current. Since there are 2 battery, we cannot say 2 battery produce 2 current. No, the current will always follow the bigger pump, because this one pump harder, 15 volt, you know, pump harder. This one E2 is a smaller pump, it's pump softer. So the current will tend to follow the dominant pump. So it will follow this way lah. Although the EMF is in opposite direction, like E2, the EMF is in opposite direction, but it is a smaller battery. It's not strong enough to overcome the 15 volt. So the current will follow the 15 volt instead of 10 volt. So for this one, for this case, it's like, I can say that for this case, it's like, what I can say is, it's like, yeah, it's like total EMF, you get positive 15, negative 10, then this is what I mean, a positive E1 and negative E2. That's why I say, even the pump, we have positive EMF and negative EMF. You understand? Look at the direction of the pump. Then this one ends up the total EMF is only 5 volt. Total EMF is only 5 volt. But in the other way, if you want the pump to work with each other, then you must connect it correctly. You must connect it correctly. You must connect it in this way. You see that? You must connect it in this way. So then it will work with each other. This is the battery E1 and this is E2. So this pump is in this direction and this pump is in this direction. This one, it help each other. This battery, both of these battery, they will help each other. So this is 15 volt, this is 10 volt. What is the total EMF for this case? If you use the loop, the concept of the loop, you will find that both are positive EMF. You will find that both are positive EMF. Both are positive E1 and positive E2. They help each other. So this pump, they all pump in the same direction. They all pump in the same direction. They help each other. You get 25 volt instead of 5 volt. Do you see that? Work with each other. Don't work against with each other. Then you get a lesser energy in the end. But if you work with each other, you get more energy to pump the electron in the circuit. Understand? Okay, that's it for positive E and negative E. Okay, so in a nutshell, what I can say is, if you have only one loop, there's only one current. There's only one current, and then there's no first law because no junction. You see that? This one it only have one current. For junction to exist, it must have three different current. You must at least you must three current. But since you only have one current for one loop, you no need to apply first law. No need to apply first law. But for the second law, since you only have one loop, then for second law you only have one equation. You only have one equation. Okay. Now for two loops, question for two loops are like this question. You have two loops, loop 1 and loop 2. So, but if you look at here, even it has two loops, actually it has three loops. The top loop, the bottom loop, and the big loop, the big outside loop, without passing the center. Actually, you have three loops here. Okay. So, for this one, the two loops case, we have three current. We have three current, I1, I2, and I3. So just like I said just now the orange, the blue, and the green. You have three different current, I1, I2, and I3. And then for first law, you only need one equation because we have two junction. For two loops, we have two junction, but you can select either junction. You can either select junction A or you can just select junction B. You still get the same equation. You see that? You still get the same equation. So just do one equation for first law. And then for second law, you have you will have three loops for you to choose. Three loops, upper loop, bottom loop, and the big loop. And then since you have three loops, you can build three equations. But you only need two. You only need to find two equations because we only have three unknowns. You see that? We only have three unknowns, I1, I2, and I3. We only have three unknowns. So you only need three equations to solve three unknowns. Okay? Understand? So first law, choose one equation. Second law, choose two equations out of three. Yeah? So there are three loops for you to choose. The upper loop, bottom loop, or the big loop. Okay. Which loop to choose? Make a wise decision. Later, I will tell you what is meant by wise decision. Now, loop is got two directions for you to choose. Either you want to go anti-clockwise or you want to go clockwise. Okay? So both accepted. If you choose any of the direction, clockwise or anti-clockwise, no wrong. Yeah? You still get back the same equation, just opposite sign. It's just like later I will explain. Yeah, maybe I can explain like this briefly. If you choose anti-clockwise, maybe you get equation like A plus B equal to minus C. But if you choose the clockwise direction, maybe you get another equation which is negative A negative B equal to positive C. You get is these two equations is still the same, just opposite sign. You understand? Because if you see, where if for the second equation I multiply -1 for both sides, I still get back the same equation. Negative A become positive A, negative B become positive B, and then positive C become negative C. I still get back the same equation. So if you want to choose anti-clockwise or clockwise, you still get the correct equation, provided if you apply the positive negative correctly. Yeah, positive negative correctly. So you ask me, want to choose anti-clockwise or clockwise, both accepted. Both accepted. It's just that both will get a correct equation. Both will get correct equation. It's just that do also wise choice. This also depend on wise choice. What I mean by wise choice is we try to prevent equation which has many negatives like this. Try to prevent, because something with negative, we normally tends to make mistake. Sometimes we forget to put the negative, then it's wrong already. Understand? Wise decision is you try to make equation like this, less negative one, like this one, like A plus B equal to negative C. This is a wise decision. This is a wise decision. If you pick the direction which is end up you get negative A and many negative terms, this is unwise. Yeah, this is unwise, because you are going to deal with many negative values, which sometimes is dangerous, because you might substitute the value wrongly. Understand? So how to pick a wise decision? Try to follow the direction of the current and direction of the EMF in that loop. Try to follow the majority of the battery direction, the EMF direction, and try to follow the majority of the current direction. As I said, if your loop same direction with the battery, you get positive E. So try to choose the direction of the loop that same direction with the EMF, and also try to choose the loop direction same direction with the current, so that you end up to have many positive E and positive IR. We try to avoid this negative E and negative IR, because calculation that involve negative values tends to be harder. We like this positive E and positive IR more. Okay, try to choose the loop direction, that same direction with the majority of EMF, and also same direction with the majority of current passing through resistor. Understand? Even though if you choose unwise direction of loop, if you choose the loop direction that go against with the opposite direction with the EMF or the current, never mind. You still get the correct equation. You still get negative A, negative B equal to positive C. If you multiply -1 for both sides, you still get back the same equation as the wise choice. You understand? So you want to choose anti-clockwise or clockwise, both are correct. Okay? It's just a matter of wise or unwise. Okay, that's all for introduction for Kirchhoff rule. Next videos, I'm going to discuss one questions on Kirchhoff rule. Thank you.